Welcome to our lesson on second-order differential equations. Today, we'll explore two powerful methods for solving non-homogeneous second-order linear differential equations, the superposition principle, also known as the method of undetermined coefficients, and variation of parameters. Let's start with the general form of a non-homogeneous second-order linear differential equation. We have y double prime plus p times y prime plus q times y equals g of x. Here, p and q can be constants or functions of x, and g of x is our non-homogeneous term. The homogeneous version of this equation has g of x equal to 0. The solution to our non-homogeneous equation consists of two parts. First, the complementary solution, or homogeneous solution, y subscript h, which satisfies the homogeneous equation. Second, a particular solution, y subscript p, that satisfies the original non-homogeneous equation. The general solution is simply the sum of these two parts, y equals y subscript h plus y subscript p. Now, let's discuss our first method, the superposition principle, also known as the method of undetermined coefficients. This method works well when we have constant coefficients and when the non-homogeneous term g of x has a special form, such as a polynomial, exponential, sine, cosine, or a product of these functions. The method has four main steps. Step 1. First, we solve the homogeneous equation to find y subscript h. Step 2. Based on the form of g of x, we make an educated guess for the form of the particular solution, y subscript p, with undetermined coefficients. Step 3. We substitute this guess into the original equation and solve for the undetermined coefficients. Step 4. Finally, we combine y subscript h and y subscript p to get the general solution. Let's see this method in action with an example. Let's solve the equation y double prime minus 3 times y prime plus 2 times y equals e to the power of x. Step 1. First, we need to solve the homogeneous equation y double prime minus 3 y prime plus 2 y equals 0. We use the characteristic equation. Our squared minus 3, our plus 2 equals 0. This factors as our minus 1 times our minus 2 equals 0, giving us our equals 1 and our equals 2. So our homogeneous solution is y subscript h equals c subscript 1 times e to the power of x plus c subscript 2 times e to the power of 2x. Step 2. Now we need to guess the form of our particular solution. The non-homogeneous term is e to the power of x. So normally we would guess y subscript p equals a times e to the power of x. However, e to the power of x is already part of our homogeneous solution, so we need to multiply by x to avoid overlap. Therefore, our guess is y subscript p equals a times x times e to the power of x. Step 3. Now we substitute our guess into the original differential equation and solve for the coefficient a. First, we need to find the derivatives of our guess. Y subscript p prime equals a times e to the power of x times x plus 1. Y subscript p double prime equals a times e to the power of x times x plus 2, substituting these into the left side of our equation. Y double prime minus 3y prime plus 2y equals a times e to the power of x times x plus 2 minus 3 times a times e to the power of x times x plus 1 plus 2 times a times x times e to the power of x, simplifying a times e to the power of x times x plus 2 minus 3x minus 3 plus 2x equals a times e to the power of x times negative 1. This must equal our right side, e to the power of x. A times negative 1 times e to the power of x equals e to the power of x, solving for a equals negative 1. Therefore, our particular solution is y subscript p equals negative x times e to the power of x. Step 4. Finally, we combine the homogeneous and particular solutions to get our general solution. Y equals y subscript h plus y subscript p equals c subscript 1 times e to the power of x plus c subscript 2 times e to the power of 2x minus x times e to the power of x. And there we have our complete solution using the method of undetermined coefficients. Now, let's move on to our second method, variation of parameters. This method is more general and can handle a wider range of non-homogeneous terms. It's especially useful when the non-homogeneous term doesn't have a nice form that works well with the method of undetermined coefficients. The steps for variation of parameters are: Step 1. Find two linearly independent solutions to the homogeneous equation. Let's call them y subscript 1 and y subscript 2. Step 2. Assume a particular solution of the form y subscript p equals u subscript 1 times y subscript 1 plus u subscript 2 times y subscript 2, where u subscript 1 and u subscript 2 are functions to be determined. Step 3. Impose the condition u subscript 1 prime times y subscript 1 plus u subscript 2 prime times y subscript 2 equals 0. This simplifies the derivatives in the next steps. Step 4. Require that u subscript 1 prime times y subscript 1 prime plus u subscript 2 prime times y subscript 2 prime equals g of x. Step 5. Solve the resulting system of equations for u subscript 1 prime and u subscript 2 prime, then integrate to find u subscript 1 and u subscript 2. Step 6. Substitute back to find y subscript p and combine with y subscript h for the general solution. Let's see this method in action with an example. Let's solve the equation y double prime plus y equals tangent of x, where x is between 0 and pi over 2. Step 1. First, we solve the homogeneous equation y double prime plus y equals 0. The characteristic equation is our squared plus 1 equals 0, which gives us our equals plus or minus I. So, our homogeneous solution is y subscript h equals c subscript 1 times cosine of x plus c subscript 2 times sine of x. Step 2. We assume a particular solution of the form y subscript p equals u subscript 1 times cosine of x plus u subscript 2 times sine of x. Step 3. We impose the condition u subscript 1 prime times cosine of x plus u subscript 2 prime times sine of x equals 0. Step 4. And we require u subscript 1 prime times negative sine of x plus u subscript 2 prime times cosine of x equals tangent of x. Now we have a system of two equations u subscript 1 prime times cosine of x plus u subscript 2 prime times sine of x equals 0. U subscript 1 prime times negative sine of x plus u subscript 2 prime times cosine of x equals tangent of x. Step 5. Let's solve this system for u subscript 1 prime and u subscript 2 prime. From the first equation, we can express u subscript 1 prime in terms of u subscript 2 prime. U subscript 1 prime equals negative u subscript 2 prime times sine of x divided by cosine of x, which equals negative u subscript 2 prime times tangent of x. Substituting this into the second equation. Negative u subscript 2 prime times tangent of x times sine of x plus u subscript 2 prime times cosine of x equals tangent of x, simplifying u subscript 2 prime times tangent of x times sine of x plus u subscript 2 prime times cosine of x equals tangent of x, factoring out u subscript 2 prime. U subscript 2 prime times tangent of x times sine of x plus cosine of x equals tangent of x. The term in brackets can be simplified. Tangent of x times sine of x plus cosine of x equals sine squared of x divided by cosine of x plus cosine of x equals sine squared of x plus cosine squared of x divided by cosine of x equals 1 divided by cosine of x, or secant of x. So, u subscript 2 prime times secant of x equals tangent of x. Therefore, u subscript 2 prime equals tangent of x divided by secant of x, which equals sine of x. And going back to our expression for u subscript 1 prime, u subscript 1 prime equals negative sine of x times tangent of x, which equals negative sine squared of x divided by cosine of x. Now, we need to integrate u subscript 1 prime and u subscript 2 prime to find u subscript 1 and u subscript 2. For u subscript 2, we have u subscript 2 equals the integral of sine of x with respect to x, which equals negative cosine of x. For u subscript 1, we have u subscript 1 equals the integral of negative sine squared of x divided by cosine of x with respect to x. We can rewrite this as u subscript 1 equals negative the integral of 1 minus cosine squared of x divided by cosine of x with respect to x equals negative the integral of secant of x minus cosine of x with respect to x equals negative ln of the absolute value of secant of x plus tangent of x plus sine of x. Now we can construct our particular solution. Y subscript p equals u subscript 1 times cosine of x plus u subscript 2 times sine of x equals negative ln of the absolute value of secant of x plus tangent of x plus sine of x times cosine of x plus negative cosine of x times sine of x. And our general solution is y equals y subscript h plus y subscript p equals c subscript 1 times cosine of x plus c subscript 2 times sine of x plus y subscript p. Now let's compare these two methods. The method of undetermined coefficients is usually simpler when applicable. It works well when g of x is a polynomial, exponential, sine, cosine, or a product of these functions. However, it doesn't work for all non-homogeneous terms, and sometimes requires creative guessing for the form of the particular solution. Variation of parameters is more general and can handle any continuous non-homogeneous term. It gives a systematic way to find the particular solution without guessing. However, it often involves more complex calculations and integrals that might be difficult to evaluate. In conclusion, both methods are powerful tools for solving non-homogeneous second-order differential equations. The choice between them depends on the form of the non-homogeneous term and your personal preference. Remember, the key is practice. The more problems you solve, the better you'll get at recognizing which method is more appropriate for each situation. Thank you for watching.